Good day, Doctor. I'm Yong Jasin, metric number 2400614 from Group 2. In this biomedical engineering design KIB2012, we study the conventional ankle foot orthosis. Here are my group members, Astrid, Isandra, and Avish. In this presentation, we have abstract, introduction, objective, design concept, result, discussion, limitations, improvement, and conclusion.
Hello Doctor, my name is Muhammad Darwish bin Muhammad Shuhaimi and I will talk about the abstract of our group project. This project focuses on the design and fabrication of a custom solid ankle foot orthosis, A4, where it was produced using conventional orthotic methods including limb measurement, plaster casting, mold modification, and polypropylene thermoforming. The final outcome included an engineering drawing and a fabricated A4 prototype. Although natural ankle alignment was not fully achieved, but overall for this project, we successfully demonstrate the conventional design and fabrication process of a solid A4.
Good day, Doctor. My name is Asri Melisande with number metric 230688878, and today I will explain about the introduction. This slide introduces the ankle foot orthosis, or AFO, which is an external biomechanical device designed to support the foot and ankle. AFOs are commonly used to treat foot drop caused by neurological conditions that affect ankle dorsiflexion. By improving foot clearance during the swing pace and stability during the support pace, AFOs help reduce the risk of tripping and decrease energy consumption while walking. However, conventional AFO designs often have limitations such as discomfort, excessive weight, and limited mechanical adjustment. Therefore, there is a need for an AFO design that balances manufacturing costs, user comfort, and functional effectiveness. Let's move on into the objective slide. This slide presents the main objective of our project. First, the device is designed to maintain proper ankle alignment and stability during movement. Second, we aim to enhance balance and reduce the risk of falls, especially during walking. Another important objective is to ensure comfort and ease of use so the user can wear it for daily activities. We also focus on improving foot clearance during walking to support a safer gait pattern. Lastly, the design aims to achieve cost-effective fabrication, make it practical and accessible for wider use.
For the design concept, we are going to focus on user and clinical requirement, design concept and justification, and methodology. Our target users are children, adults, and elderly people who have difficulty walking due to problems with the nerves, muscles, or bones. For children with cerebral palsy, they often struggle with movement, balance, and posture. They may walk on their toes, bend their knees, or drag their feet. And AFO helps improve leg alignment and makes walking more stable. For adults and elderly people, walking problems can come from aging, injury, or disease. They may have foot drop, weak ankles, and poor balance. The AFO helps by supporting the ankle, lifting the foot, and reducing the risk of falls. The AFO is designed to control and align the ankle. The ankle is kept close to a 90-degree position, which helps with toe clearance and balance. Other than that, the stiffness must be correct. If it's too soft, it won't support the foot. If it's too stiff, it can limit the movement. The AFO should be lightweight, comfortable, and able to support body weight. Not forget that it should fit into regular shoes and be made from strong, safe material to improve balance and safety. We look at two AFO designs. The first is the solid AFO. It gives strong ankle support and prevents unwanted movement. The second is the posterior lift spring AFO. It is more flexible and helps lift the foot during walking. This design is suitable for mild muscle weakness. Our final choice is the solid AFO. It provides maximum ankle stability and improves knee alignment, which helps reduce falls. This design is best for users with severe weakness. The AFO supports the lower leg and foot, keeps the ankle slightly upward, and gives good side support. It helps with heel strike and toe lifting. Velcro straps make it easy to wear. The material used is polypropylene. It is light, strong and durable and can be shaped for a custom fit. For the manufacturing process, we use a conventional method. This method involves several steps, from leg measurement to the final product. First, we measure the leg and mark important points. Next, we make a negative mold using plaster. Then, a positive cast is created and left to dry. After that, the cast is modified and smoothed to get the correct shape. The plastic sheet is then heated and molded over the cast. Finally, the AFO is trimmed, polished and fitted with straps to make it comfortable and secure.
I will present result and discussion part in this presentation. Let's look at our result. The figure in this slide is the finalized solid R4 design. The orthosis was designed with a rigid structure to restrict plantar flexion and provide medial lateral stability for drop foot management. Moreover, below knee measurements were taken to guide patient-specific R4 fabrication. Measurements were referenced from the tibia tuberosity down to the lateral malleolus at 5 cm circumference and diameter measurements were collected to define shell contouring, trimline positioning, and comfort fitting. Diameter at the lateral malleolus was not measured due to anatomical geometry. After the fabrication process, this figure shows the final fabricated solid alpha from three perspectives: the left lateral view, anterior view, and right lateral view. These views will highlight the shell contouring, trimline positions, and overall structural symmetry of the orthosis. Now let's look at the discussion part. Do we achieve our initial goal? First, structural integrity was successfully achieved. The thermoform polypropylene shell maintained its shape and rigidity throughout handling and fitting, indicating that the material selection and overall design thickness was appropriate. Second, the R4 provides adequate medial lateral stability. The rigid solid design effectively resists the excessive ankle motion during stand phase, which is consistent with the primary function of a R4 in drop foot management. Third, material performance met expectation. Polypropylene offers a good balance between stiffness and low weight, supporting ankle stability while minimizing added limb mass. However, neutral ankle alignment was not fully achieved. This reduced swing phase toe clearance and limited overall biomechanical performance. In summary, the design concept itself was successful, but the functional outcome was partially limited by fabrication error, specifically inaccurate ankle positioning during casting rather than flaws in the design. Why does the casting alignment error occur? During negative casting, the ankle was not maintained at the neutral 90-degree position. This resulted in a plantar flex high heel alignment in the R4. Consequently, swing phase toe clearance was reduced, negatively affecting guide efficiency. This highlights that accurate ankle positioning during casting is critical to achieve optimal R4 biomechanical performance. Besides, we compare the developed solid R4 with existing commercial products and literature-based designs. Compared to commercial thermoplastic R4s, the developed R4 shares similar material selection and stability objectives. However, commercial devices benefit from standardized casting and quality control, allowing more accurate neutral ankle alignment and improved swing phase toe clearance. Advanced designs reported in the literature such as carbon fiber and additively manufactured R4s provide superior energy return, reduce weight, and improve gait efficiency. However, these devices require specialized materials and equipment, making them less accessible and more expensive. In contrast, the developed solid R4 prioritize stability, affordability, and commercial manufacturability, making it suitable for resource-limited clinical settings. Although biomechanical performance was partially limited by fabrication error, the design remains conceptually aligned with established solid R4 principles. Several limitations and challenges was identified in this design. The most significant issue was casting alignment error where the angle was not held at neutral, leading to a high heel configuration in the final R4. Additionally, polypropylene thermoforming is a one-time process, meaning errors such as overheating or uneven stretching can cause tightening or structural defects. especially when handled by non-specialists. Once fabricated, the alpha also lacked adjustability, making alignment correction difficult without remanufacturing. Finally, the inherent rigidity of a solid alpha may increase working effort compared to dynamic design. Then I will pass to next member to continue the presentation.
For future work, 5 main improvements are proposed. First, the ankle alignment accuracy can be improved using alignment jigs or goniometers to ensure a 90-degree position during casting. Second, use alternative materials such as carbon fiber to provide better energy return. Third, adopt the digital methods like 3D scanning to improve accuracy and reduce fabrication errors. Fourth, consider the semi-rigid or articulated A4 design. And last, perform the objective evaluation to assess functional performance. Conclusion, this project successfully demonstrates the fabrication of a solid ankle foot orthosis using conventional polypropylene techniques. The final prototype provides strong structural stability and motion control. However, alignment errors during the casting phase result in unintended plantar flexion. This limitation impact the functional performance, but overall, the project greatly strengthened our understanding of biomechanics and the importance of fabrication accuracy.
Thanks for watching our presentation.